Seminar is realized in collaboration with the Northwestern University as well as Koç University and Istanbul Bienali. So we have many guests from other departments of universities such as artistry, physics, mathematics, and oceanography. This is a two-day program. So the first run is today, and tomorrow we're going to unfold starting in the morning. And this seminar is looking at the aesthetics in relationship waterways as well as knots and their knot theories in general. And how these terms can be related to art and artists' practices will also be discussed. So the first speaker is Emin Özsoy. He's a professor and the head of physical oceanography at the Institute of Marine Sciences, Middle East Technical University. His research and expertise in oceanography is focused on basin and shelf circulation, wave and tidal motions, tsunamis, strait dynamics and outflows, ocean modeling, double diffusive convection, isotope tracers, ecosystem dynamics, as well as regional meteorology and transport. Özsoy is the author of major research, review papers, and essays included in books and published proceedings. He has been a visiting professor at the University at Bologna in 2014-2015 and Harvard University 1989-1990, amongst other universities. So please welcome Emin Özsoy. Thank you so much.
But unfortunately didn't play the movie, so we switched back to the PC. Okay, so this is what I'm going to present, and the authors, my students, and other people that we collaborate with in this work are listed here. So the subject is very fitting for the Saltwater Biennale. And I will talk about, although I work in other salt waters, I'll be more concerned with the Turkish Straits, the Turkish Straits system. I say a system because it really is a coupled system starting from Black Sea to the Mediterranean of different elements in it. One of them is Bosphorus, for example. The other one is the Sea of Marmara, Dardanelles Strait. They are all small elements coupled together, so there's really no way to cut them apart as single identities. So the salt water that's actually around us here is the Bosphorus, and the Bosphorus controls the flow of water from Black Sea to the Mediterranean on the surface. But at the bottom, there's also the Mediterranean water going in the reverse direction. From the Mediterranean, first to Marmara Sea and later to the Black Sea. And you see in this picture also the recent social problems which I'm going to touch upon. Not only social, but the development problems that we are facing today. For example, the green forests, which appear red in this picture in the north, are being plagiarized by building roads through it. So pretty soon we may not have this red as wide as it appears here. And in the south you see the Istanbul, city of Istanbul, concrete on both sides of the strait. On the Asian and European sides, sprawled on two continents. And in the south, you see this feature, the dark image, which is the water coming from the Black Sea and exiting into the Marmara Sea in the form of a turbulent jet. And you see its mark on the surface. It really is on the surface. And it brings nutrients from the Black Sea to the Marmara Sea. And that's why Marmara Sea has been basically destroyed by this since about 10, 20 years. Now we are even considering to build a canal Istanbul. This is what so-called crazy project. So this is just the introduction for you to realize what's happening in the region. But I would like to begin, since we have here very distinguished guests on the fluid dynamics and mathematics area. I'd like to mention that all we are doing is trying to get solutions of basically fluid dynamics equations, which are Navier-Stokes equations, which are known from 18th, 19th century. But they are, I must say, they are very productive equations. They are very simple equations, but actually I was going to put one of the titles of a paper, simple looking in parentheses. Simple looking equations, which produce a variety or a rich variety of many problems that come out of these equations and we observe in everyday life. But we are still not able to understand whether these equations have unique solutions. So the Navier-Stokes equation that has been offered from the Clay Institute of Mathematics in US, a $1 million prize actually for mathematicians to prove of uniqueness of the solutions of Navier-Stokes equations, which has not been proved to this day. Okay? And as you will remember, recently Perelman, who solved one of these prize problems, first refused to get this prize. Anyway, this is just the introduction to what we are actually looking at. And the equations are actually simple equations like that, some conservation equations, basically, that putting in proper variables, you can have them in the form of continuity equation, the momentum equation, heat transfer equation. They are basically all the same of given quantity being conserved in a material volume of the fluid. Anyway, I'll not go into the details, don't worry. Okay, so, but as I said, this creates a rich plethora of many problems that you can face in everyday life. The basic character of these transport equations is that they are nonlinear. And nonlinear processes, as you would know, defy certain simple principles like superposition and basically also what we are dealing with in the ocean they are open systems, so you cannot really isolate a piece of the ocean and look at it. But still they are complicated problems where your theoretical or models or equations are not sufficient. In fact, we have a predictability problem that's associated with nonlinear processes that you cannot actually predict the future very easily. So, not very easily, and your models always drift away from the truth in time. So what we are faced with is also we have to use the observations, very strong observations, which is actually a Galilean requirement for the scientific method, which was discovered in the 16th, 17th centuries. Okay? So we are faced with this kind of unknowns, and we are now using different techniques like ensemble forecasting and Bayesian techniques to face this problem. And as you see some examples, in the global ocean we have a variety of flows that are very specific, coherent structures where you can identify an eddy for almost many years. So I would like to, from this introduction, I'd like to now draw upon what happens in our surroundings and actually start with the historical beginnings of the science of the seas. Initially, the first ocean interest, of course, started with discoveries of Christopher Colombo, etc. And as I mentioned 2 days ago in the panel, the first oceanographers were essentially observing people who were the initial geographers. They write in the Mediterranean, the old world, for example, they write stories which were called isolarios, island descriptions, the traveler's notes, okay? This is how it started. And Piri Reis, whom you may know, one of our people, from local people, who was a captain of the Ottoman Navy afterwards. Initially, he was a privateer, and he ended up going to the Indian Ocean with a competition with the Portuguese afterwards. But he was a captain. He used he collected, or people were passing these documents, maps of the Mediterranean first, and then he combined actually he refers in his map, a map from Columbus that he took and synthesized and made the first world map of the Atlantic Ocean. And 10 years later, he also tried to construct the Pacific Ocean. Anyhow, this is how it started of course, map making is much more earlier than that, but this is the first synthesized map. And then comes Galileo with this scientific method. The tides, at Galileo's times, Galileo had a theory of tides, for example, but it was essentially not related to the moon. It was a theory of tides that he thought it was because of the Earth's motion. And he actually made the equations and so forth. He solved them, but it was not correct, okay? And then comes Isaac Newton in 1642, 1727. He came up with the first scientific theory of tides. And actually, I would also add that Piri Reis, just 1 century before him, had an idea by observation that tides were related to the moon. As a captain, he observed them in Gulf of Gabes in Mediterranean, and he noted that. But of course, he was not a scientist, and science was not even in appearance then. Okay. Then comes, for our interest, for the Turkish Straits, Luigi Ferdinando Marsigli, who was a 21-year-old gentleman from Bologna, who joined the Venetian ambassador to Istanbul with a ship. When he was coming to Istanbul, he made observations of density. Actually, there was no concept of density at the time. It was not referred to as density. So he measured the weight of water, so to speak. And as he observed this, he realized that there must be something funny in the Bosphorus. Okay, there's also listed other works of him here, but he's this character who actually was involved later in the siege of Vienna by the Ottoman Turks. He served on the other side, the Habsburg, as a spy, but that doesn't stop him from being a scientist, of course. Because in those days, people were combined scientists. Okay, anyway, he wrote also a book on the military state of the Ottoman Empire for the good of the Habsburg. Okay, so he came to Istanbul, and the first thing he did was make beautiful notes of the hills and the forests and the fish, and observe. For the first time, he found that by talking to the fishermen and local philosophers at the time, that he discovered there was a flow beneath the Bosphorus. And he tried to tie this to the sea level difference, actually, but he couldn't measure it. But he had the right idea, right there. And he writes here in Turkish, dibinden akar, which means there's a flow underneath. And this is the first reference to it in written literature, that it was actually ignored. I mean, ignored for 300 years. His work was ignored for 300 years and discovered only in the last century. he is like the National Geographic of the time. You know, he writes in Arabic, Turkish, French, Italian, and Greek letters, the name of fish, and makes beautiful pictures like this. So after discovering the undercurrent in the Bosphorus, he tried to measure it. He simply took a rope and put a blob on it, bob, and sink it to the Bosphorus, and he observed that the current was initially towards the south and then later turned towards the north in the Bosphorus. Actually, this was, it turns out, although we discovered this only 300 years later than him, actually there was reference to it in 6th century AD by local people, which was also, there's an article by Manfred Korfmann, who is the archaeologist of Troy, about this. So people already knew about it, but come to 20th century, our first scientists, who were actually biologists, and didn't have the equipment to measure or something, they couldn't measure it. So they were questioning whether actually there was a Mediterranean flow or not. In the 20th century, all these things were known, but nobody carried this information. So the outstanding thing about Marsili is that he went and actually made a laboratory experiment in Rome 1 year later after his visit to Istanbul. He simply put two water masses in a divided tank with light and heavy, dense and low density waters, and separated them with a plate. And he showed that if you put a hole on the top of this plate, nothing happens. Actually, basically, the fluid will pass to the other side by diffusion, and that's all. But if you pierce a hole on the bottom, everything changes, because now you have a pressure difference between the two bodies. So you tend to generate this red current on the bottom, and there's a compensation current on the top. So basically, oceanography actually started in the Bosphorus in the 17th century, okay? And he had the first theory of density currents. What he discovered more is he made a map of the currents, essentially currents coming from the north to the south, but he discovered there was a recirculating zone in the south of Bosphorus, which is also present today. And he described it, but there's also past references to it from 2nd century AD, that this, what's his name, the Dionysius of Byzantium, who described the Bosphorus and its currents, and how ice flows come from Black Sea and hit the houses. He described the climate change aspects, okay? And the most important thing about this is that this recirculation is the source of richness of Istanbul, because it bring all the fish, the bonito fish from Black Sea, and these fish were trapped in the Golden Horn, which was called the Keras at the time. And this was the source of the fish trade of Byzantium and later of Ottoman empires. Okay, so Marsili essentially even talked about that. And even in the 1950s, these pictures show a big contrast to today, that there's large amounts of fish that were caught in the Bosphorus, in the Marmara Sea, when it was in a much better condition. And this fisherman, he's a photographer, he's an artist who documented the fishermen of Kumkapı. And until recently, until the 1950s, there were such installations on the Bosphorus where you would just put down a net and catch large amounts of fish by just putting a net down. And a whole family would live in such installations with their children and so forth, and live on this. So today, we come to today, and just about a month or two ago, we had this cross-Bosphorus swimming competition. And this is much livelier now, but I was surprised, actually, to see this, because it's right at the point where there's this hydraulic controls that I will talk about. So they were very courageous to swim across there, actually. Okay, so I talk about a bit about Bosphorus. This image, these two images, one of them is a section of temperature across the Bosphorus. The other one is a salinity transect. But they are not model results. They are observations made by about 174 drops of an instrument, a free-fall instrument. And from this, we synthesize a very high-resolution cross-section across the Bosphorus. All these colors represent different water masses. For example, the blue there is the cold water mass of Black Sea that's trying to get into the Bosphorus. And the black dots are the interface, denote the interface between the upper and lower layer. So the two flows interact, and there's a lot of modifications as they cross the Bosphorus because of entrainment, turbulent entrainment from one layer to the other. So they are being diluted or getting more dense or otherwise. This is a dynamic system. Despite of this mixing, it responds very rapidly to winds, so you can have blocked flow conditions. Either the upper layer or lower layer can be blocked. And this shows when you have a sill. Actually, I should go back and to show you these two sections. One of them is a contraction in the Bosphorus, the narrowest point of Bosphorus, the first one. The second one is the sill, where the flow, the lower layer flow, comes and overflows like a dam into the Black Sea. Okay? So this controls, for a sill, for example, simple solutions like this show you that sometimes the flow will come, feel the bottom topography, but pass without too much change. So the blue line is the free surface. The red line is the current magnitude. So you can see that it's disturbed by the bottom topography, but not too much. There are other cases where you can have controlled flows, and this control is represented by this composite Froude number, which is essentially analog of Mach number for aerodynamics. So if you cross Mach number 1, for example, the speed of sound, then sound you leave behind, right? And in here, water waves can go in either one direction, depending on the Froude number. Anyway, in this kind of flows, the flow comes and thins out, passing on to the other side, which means it accelerates. It has a big speed, and that's called supercritical. Only this detail I want to say, and this is a solution where the information actually is transferred in both directions, but then after the flow is controlled, it's a unique solution. It's only one solution where the depth and the current is essentially linked by this Froude number argument, and it's a single special solution in a family of possible solutions. Okay. So what does this have to do with Bosphorus? In the Bosphorus, actually, there are two controls, as I mentioned. One is the narrow point of Bosphorus. The other one is the sill, where both this Froude number criteria are satisfied. And this kind of a flow is specified as a maximal exchange solution, where you have this kind of a configuration of the interface. As we have seen the sections in the Bosphorus, they are very similar to this. And we try to demonstrate this by the Turkish tea glass, which has a narrow section in the middle, which is like a sill. And as you can see here, so the flow is actually controlled over the sill. which makes it flow at a slower speed so that you don't burn your throat. I think it's a very ingenious idea that was developed over the many times. So we have constructed models of the Bosphorus. This is, for example, work by 3D models, where you can see very similar flows that I showed the measurements in the measurements. And in the bottom figure, you see the turbulent diffusivity. So the models already have turbulence parameterized in them. So we can look at the energy aspects of it. And this shows the energy dissipation by these turbulent structures. And you will see maximum of turbulent dissipation in the south of this southern entrance and north of the sill in the north of the Black Sea, in entering the Black Sea. These are features, what we call hydraulic jumps. We talked about hydraulic effects, and this movie shows what we mean. Okay, so this special solution, essentially we have subcritical flow coming. There's critical on top of the sill, and it narrows down, thins out, where it speeds up. So it's a supercritical. And then as you try to change the sea level on one side, you essentially create a hydraulic jump, which is coming now. Okay, you see the hydraulic jump. And when it comes, the sea level increases, then it will submerge the flow down. Okay, where do you see hydraulic jumps? You must have seen this in the bathtub, for example. When you take a shower, in the bottom you will see something like this circular hydraulic jump. Or when you are out in the Bosphorus, you will see the speedboats. On the wake is essentially a hydraulic jump, where the flow accelerates, but it cannot maintain, it's not sustainable. So it has to dissipate some energy, sudden dissipation of energy, and that creates the hydraulic jump. So I have some movies to explain. Such flows, for example, down a slope, and then you create the hydraulic jump, or a bore. What? Sorry? It doesn't show. Must have come out.
Oh, okay, thank God it's not the bowl.
Can you put it now?
Yeah, of course.
Cannot see. Okay. Okay. Yeah, because. Okay. That's okay. No. Can you put this down? Sorry. Sorry, but maybe that may have waked you up. Okay. So I should try to show it again. So this is the flow accelerates, as you see here, and then you see the hydraulic jump. Okay. Other examples is this hydraulic jump, for example, in the lee of mountains. This is Sierra Nevada in US, where you have a flow coming and dropping down the hillside, and then you see the hydraulic jump with the clouds. And this is a picture of measurements showing the turbulent structures in the hydraulic jumps. Okay, and then where you see some fun. Like this, okay? Riding on a hydraulic jump must be quite exciting, as you see here. Or the surfers, you can think of this as a hydraulic jump because it's a wall of water that's coming and collapsing like that. And apparently some fish, dolphins, like that very much, so they enjoy the same thing. And that's a quite an artistic show, I would say. Okay, and what we try to understand of the Bosphorus, we extend to the entire system, the coupled system with the two straits and the Marmara Sea, and we have also the coupling between the Black Sea and the Aegean Sea now. But the problem gets very complex, of course. It can only be solved on supercomputers because you cannot possibly resolve what's happening in the Bosphorus, which is an essential part of the story. So we do this on supercomputers, although we don't have too much time for that. And there was an EU initiative called PRACE, where we use the computers to do this computation. So it shows some details, and we try to vary the cross flow and see how this circulation in the Marmara is developed as a result of this Bosphorus flow. And we have a series of other models that I'm not showing here, a sequence of different models. And here's a vertical section of the Turkish Straits. As you see here, the upper layer flow is only 25 meters thick. And everything is happening there. All the ecosystem is in there, okay? And what you see is a dark shadow there on the Dardanelles side, in the lower layer, is the water coming in from the Dardanelles. And that's the only source of oxygen for the Marmara Sea. Because oxygen cannot penetrate from the upper layer, because it's a very stratified, sharp stratification, so there's the danger of Marmara Sea becoming like Black Sea eventually. There will be no oxygen. Right now, there's enough, well, I shouldn't say enough, but very low levels of oxygen already in the Marmara Sea. So it's in the hypoxic level. It's not anoxic, but if we introduce more nutrients from the Black Sea, there's a danger that it can turn into an anoxic basin, just like Black Sea. Okay. Today, what we observe from satellites, we can observe chlorophyll. And although we know Black Sea is a very highly productive sea, Marmara Sea is even more. So you see yellow in the Aegean and Black Sea, but the Marmara Sea is all red, which means a higher level. And then you see the jet bringing in new water to the Marmara Sea, and this jet is essential part of the system. And a recent picture from International Space Station just this year shows a red tide bloom in the Marmara Sea, which did not happen 10 years ago. Now we are becoming more and more polluted and more nutrients coming from Black Sea. So we are seeing all kinds of effects of this, including mucus, like in Adriatic Sea, in other seas. We are facing this problem, which shows that although despite this beautiful picture, Marmara Sea may be dead since 20 years. And we are making it more dead, okay, trying to make it more dead. Okay, and then this is an aerial picture showing the same. This orange-colored stripes are what we see in the other picture. And they are, you see, they are being effectively mixed by all these jets and eddies. This is churning them and making more serious problem. A recent picture by an Italian astronomer on the satellite, astronaut, okay, shows these features of the flow, the jet, and what is being carried from the Black Sea. And you can also see this road that's being constructed, the third airport, third bridge, etc., which is very critical to the whole liveliness of Istanbul. So Istanbul is destroying its last reserves, basically. And the population from 1960s, this picture shows you how Istanbul was when I was a kid. And now here we are in the Star Wars scenario, where we will have taxis flying over each other very soon. Okay, and then we can have a population of 30 million, like Cairo. I don't know what will happen then. So we tried to make also a simulation of the Canal Istanbul and its effects we found that there's is a different regime. It's a weak coupling between a small new canal and a very powerful Bosphorus. I will not go into the description, but we know something about it. And what we know is that we are adding 4 new rivers. Almost the amount of water that will be added is equivalent to 4 new small rivers. And we are threatened by the earthquake as well, which experts say that it will be coming in the next 15 to 30 years. And we are not prepared for it. And the sea level rise is another thing. In the next century, perhaps we can face a sea level rise of maybe 1 or 2 meters, which is threatening not only Istanbul, but the whole of the world. But it's more stronger in the Mediterranean. So that means we have a higher risk. And there's no answer to these questions. Thank you very much. So I'll be pleased to answer any of your questions.
Is there a scaling that you can do? And the question is, you study these flows with computational fluid dynamics. Can you make a scale model? Is there some scaling that you can do to study this in experiment?
Yes, you can do scale models only if you have a turning table, because everything is geophysical fluids, so you need to have taken into account Coriolis effects. It's not so simple to make, but I think it would be very nice if you could make it. Or we could make it together.
I suppose I can follow that up. The world's largest spinning table is at Grenoble.
Yeah.
It's got a 13-meter diameter. So given the length of this system, what sort of scaling ratio do you have to use?
I have no idea right now, but I think it can be. I know this Grenoble, and it's open to researchers actually to propose experiments like that. Maybe that's something to do. Could be something, but of course we have to take a 2-layer stratified system too. So scaling is not unique.
No.
You have to adjust the scaling such that you will have this 2-layer flow without disturbing it too much, you know, and even though you will have molecular diffusion, that may not be enough to sustain this stratification. That's not so easy.
Can I ask a second question then? So in terms of sea level rise, do you think then the Mediterranean will rise higher, as it were, and therefore the nature of the flow through the straits would change?
That's true. The nature of the flow will change, but also the sea level rise is also in the Black Sea, which receives more water actually. So we don't know the answer, but there's a submitted paper. I'm giving you some indication that the Mediterranean rises higher than the world average is true. And even in the world, they are suspecting this. This figure is from a recent NASA report, NASA. And they have actually made calculations that show 8 centimeter rise, global average 8 centimeter rise in 23 years. This is just a result that they announced last week. And they are suspecting it's accelerating. For many years, actually, they were saying that the sea level rise could not be a serious problem because carbon dioxide will level off and, you know, it will slow down. But now they are thinking maybe it's accelerating. So it's not a clear question. So thank you very much.